Okay, the recording starts. So the time
Okay.
is yours.
Thank you very much for this opportunity, Danuta and Gianni, that both of you organized this very interesting webinar today. As Danuta told, I am using my tablet for this presentation, so I am unable to assume any control. I just can share my tablet, my presentation with all of you. What I'm going to do now, just some minutes to allow the condition. I don't know if you can see my presentation now. Please tell me if you see my slides, because I cannot see if it was a correct communication. Okay, perfect. So, as Danuta said, my presentation today concerns the applications of fast field cycling NMR relaxometry in environmental science. Let me say that this is quite a very interesting argument, not because I'm doing this for my research, but because we need in environmental science tools to understand environmental quality that is related to soil quality, water quality, air quality, sediment quality. So what I'm going to do now is to show which are the main lines, the main approaches that are used to understand what we can do by using the fast field cycling NMR on soil science and other types of environmental relevant materials. So I know that we are in meeting where all of us are NMR people, so this is simply a slide showing which is the relationship between the normal spectroscopy and the relaxometry. So I like this slide because it is really, let me say, didactic from this point of view, and it shows that what we have in NMR spectroscopy, we also have in NMR relaxometry, in fast field cycling relaxometry, the preparation, evolution, and acquisition. But apart of this, let me say that we have different possibilities to monitor the FFC NMR relaxometry results. One is by looking at the relaxograms, and one is by looking at the NMRD profiles. So in both cases, we have different and complementary information that in terms of environmental applications are very, very useful. Let me say that, for example, by using the relaxometry, in particular the FFC relaxometry, we can, for example, monitor the dynamics of nutrients and contaminants in water and in soils. We can monitor the behavior of natural organic matter. That is a very interesting point, because natural organic matter is directly related to soil fertility. So actually, to know how the natural organic matter behaves in terms of relaxometry gives a lot of information about its fate and then in the transformation of soil fertility. Then, for example, NMR can, in this case, FFC NMR relaxometry can be used to understand soil erosion. I will show you how, and to give information about environmental remediation technologies. Let me start with one of the main problems that we have in the environmental science, that is soil erosion. Let me say that everybody knows what is a soil in terms of, when I teach soil chemistry, the first thing that I say to my students is that the soil is a living organism. It is made by different components that are organic and inorganic, and inside the organic components we also find the living organism. And from this point of view, when we speak about soil erosion, we are speaking about a problem that concerns the consumption of soil due to the anthropic activity. And together with, of course, other environmental problems, such as the wind, the climate, and so on. So one of the ways, let me say that up to now, there is not a real good way to monitor soil erosion, or better. We can monitor, but we need to collect a lot of information. So, for example, we need to monitor pH changes in soils. We need to monitor texture changes in soils, and so on and so on. Also, for example, the amount of organic matter changes if soil is contaminated or is eroded. So, as you see, we have to monitor soil erosion by using many different and sometimes very difficult to understand techniques. So the idea is, why not to use fast field cycling NMR relaxometry? That is a technology that we can apply directly on very complex systems. So we do not need to, for example, to isolate organic matter from soils. We do not need to isolate the inorganic part from soils. We can monitor the soil as a whole. That is very important. But one of the parameters that is used to monitor soil erosion is what you see in this slide, the connectivity. That, as it is written here, it is taken from a paper that is cited there in the slide. It refers to processes that involve transfer of matter and energy inside between different elements of a system. That means, for example, transport of water from a point to another on a surface. But there is not, let me say, quantitative way to measure this connectivity. So we think that FFC relaxometry can be used to monitor the connectivity from a quantitative point of view. Let me show which is the idea behind this. We can define two different types of connectivity. One can be indicated as a structural connectivity, that is the extent to which landscape units are contiguous or physically linked to one another, while that means the transport of the physical transport, for example, of water from a point to another. And we can also define the called the functional connectivity. That is, let me say, an idea of connectivity that is much more molecular than the one that I defined before. This functional connectivity is more or less related to the way how water can be interact with the soil surface. So in which way, the question is, in which way, after we have given this definition, we can try to measure these structural and functional connectivities? Well, if we go to the investigation on the soils that are dispersed in water, we can obtain this relaxogram. This is one relaxogram that was obtained by suspending soil in water in a ratio 1:3. And as you see, we see this very nice, let me say, blob, where we can distinguish different type of waters, that are those that are very strongly bound to the soil surface, and those water molecules that are freely moving. Then we can do a mathematical operation by extracting an empirical cumulative frequency distribution from this relaxogram. What is in this empirical cumulative frequency distribution? We can distinguish three different zones, where the one that is called TA refers to the very strongly bound water, while the one that refers that is indicated as TB is the part of the cumulative frequency distribution associated to the freely moving water. Let me say that here we do an assumption. That means that we assume that the 1%, the maximum of the TA is 1%, and 95% is the TB. That means that we can change our numbers, changing our assumption. So this is the limit of this approach. But by using this approach, we can measure the ratio between the TB and the TA, and this we can say that this ratio is an index of the functional connectivity, just because from an ideal point of view, the TB is related, is the relaxation time of the bulk water, while the TA is the ensemble of the relaxation time of the strictly bound water. That means that if we increase the amount of bulk water, we also have an increase of the functional connectivity. That means that water moves more freely inside the system. And from an erosion point of view, that means that we are going from a sandy loam soil, for example, to a sandy soil that is an eroded soil, where water can move much more easily than in the clay soils. Clay soils are also other, let me say, soils that can be considered eroded, because if we consider the movement of water from the top to the valley, then we have to think that in this water movement from top to the valley, we have also a movement of soil particles. That means that the soil that is on the top becomes sandy, while because of the sediment movement, the soil that is on the valley will become clay. So these are the two extreme conditions for soil erosion. In this case, so that means that if we are in a situation where we measure the functional connectivity on the top of a mountain, for example, of a hill, then we can have an increase of this index when we have soil erosion. While if we look at the bottom of the hill, we have the other way around, because in that case, the amount of small particles inside the soil increase. That means that water remains much more strictly bound, and then we can have a decrease of the FC index that it is shown in this slide. But that is not all, because another index is what we call the structural connectivity index, that we associate with the slope of this empirical frequency distribution. So also in this case, the change of the slope can give an information about how is moving soil erosion. Okay, so once we have these parameters, we can say that we can have two numbers, two indexes, two quantitative indexes that can be used for measuring soil erosion. erosion. Now, why it is important to have these quantitative measurements? From, let me say that usually we realize that a soil loses its fertility when we see a decrease of the food production. So then we do analysis of the soil, and for example, we see that there is a nitrogen missing, there is a change in the texture of the soil, and so, the change of pH, and so on and so on and so on. But that means that we are doing analysis to, let me say, a soil that is already that has already problems. While if we are able to quantify earlier the erosion to which the soil is subjected, we can program intervention for repairing, let me say, this soil. Also, if we want to program, for example, at a political level, we want to program how to use the solutions for soil restoration, then we have to provide simple numbers. We cannot, let's say it is much more easy from a political point of view, let the politician understand the numbers than qualitative discussions that are very convincing from a scientific point of view, but less convincing from a political point of view. So that means that these parameters can be very important. The only problem that we have in measuring these parameters are related to the assumptions that I gave you a few minutes ago, and to the fact that fast field cycling relaxometry is fast field cycling. That means that we change magnetic field, and we do not know if there is an effect of the magnetic field on these numbers. To do this, to solve this problem, to answer this question, we did a series of analyses, and we discovered that both indexes are independent on the magnetic field. This is the graph that we obtained, and as you see, the structural connectivity index gives an average value of 0.96, while the functional connectivity index gave average values of 27. What changes between these two different type of measurements is the error that you see. There is a wider scatter in the functional connectivity index as compared to the structural connectivity index. And this larger scatter that you observe is probably due to the assumption that we have considered in measuring the functional connectivity index. So we are still in a situation where we should still prove the efficiency of these indexes, but let me say that we are going on the right way, because before the lockdown all around the world, we obtained a very nice result on different soils, and we will show that these indexes are really related to the different extents of soil erosion, which is another very common problem in environment, always related to soil problems. As I told you at the beginning, we can say that one of the most important components of soil is the organic matter. This because organic matter is directly related to soil pH, is directly related to soil structure, and to the diffusion of nutrients towards the plant roots. So one of the problems that we can encounter in soil analysis, in soil problems, is related to the changes of the nature of the structure of organic matter, which directly affects the behavior of the nutrients and water transportation in soils. And among the different, the several problems that we can have in soils, we can encounter the wetting, drying situation. Wetting and drying means situations where we can have very high temperatures and very humid conditions, which alter the conformation of the organic matter in soils, and then can alter nutrient dynamics in soils. We had different experiments. We did different experiments by dissolving fulvic acids. Fulvic acids are the soluble, water-soluble part of the organic matter, what we in soil science define as the dissolved organic matter, which is really important from a microbiological point of view and from a nutrient point of view. I was saying that we dissolved fulvic acids in water, and we analyzed these different solutions of fulvic acids by changing the temperature of the system. And what came out from this experiment was the so-called water hysteresis. That means that, let me say, if we heat the DOM solution, dissolved organic matter solution, at, for example, 50 degrees, we have a relaxation rate value. But once we come back to 25 degrees, then we are cooling the system. Then the relaxation rate that we obtain is different from the one that we measured at the beginning. So that means that because of the heating and the cooling, the conformation of the humic matter, or in this case of the dissolved organic matter, changed, and so also changed the strength by which the water is bound to this dissolved organic matter. Why this is a very important environmental problem? As I told you, if we change the strength by which water is bound to the dissolved organic matter, then we can have a problem in the exchange of nutrients from the organic matter to the water, and then we can have a problem in the movement of nutrient towards plant roots. That means that we are lowering the fertility of soils. So these type of experiments can show how to monitor nutrient dynamics in soils, and eventually how to remediate these problems if we have a thermal excursion, a very high thermal excursion. Then let me say that another very important problem that we have in soil, I'm speaking about soil because actually I was 30 years ago an organic chemist, but since a long time I'm a soil chemist. So soil is the my field of expertise. And one of the main problems that we have in soil is soil contamination. Soil contamination that can be obtained by using heavy metals or also organic materials. Let me say, I'm thinking in this moment to the polycyclic aromatic hydrocarbons, for example. So there is a very important, let me say, needing to find technologies that can be applied to remediate soil pollution. Not only soil pollution, but also water pollution, of course. And one of these technology uses what you see in this slide that is called biochar. That is simply a carbonaceous material obtained by using pyrolysis of biomasses. And as you see from these photos taken at the microscope, biochar is a very porous system. That is also the reason why I like to study biochar by using the FFC NMR relaxometry, because this is the real, a very ideal target for monitoring water movement by FFC NMR relaxometry. By using this if we put this biochar inside the soil, we can have a very, let's say, very big improvement of soil fertility. One of the reasons is that the biochar increases water retention in soil by changing soil structure. This is an example of what we have done by measuring the strength by which water is retained in soil that are added by different amounts of biochars. And also there are also effects on other soil properties such as the pH, the cation exchange capacity, and so on. But how we can use biochar to monitor the environmental pollution? One of the maybe especially the Italian people that are following this webinar know that in Italy there is a very big problem in the northeast of our country that is related to the so-called PFAS, that are organic pollutants containing fluorine. These are really present everywhere, and even the water is not drinkable at all. So here in this part of Italy, we are looking for technologies to remediate soil pollution and water pollution by PFAS. For this reason, we are trying to understand if this biochar can be applied to trap and to remove these organic pollutants from soils and water. To this aim, we have done some experiments on 19-fluoride NMR that you can see in this slide. This is the model pollutant that we have used, and all of us dealing with FFC NMR knows what is this material. This is the guard that Gianni is providing to all of us as a cooling agent for the relaxometers. And as you see, this is the typical S-shaped, Lorentzian-shaped NMRD profile for this liquid. But how this profile becomes when we use biochar? Well, what you see is reported in this slide. What the answer is in this slide, where we suspend the three different types of biochars in a garden. And the S-shaped curve that I showed you before changed completely. Let me spend a few words on these three different biochars. APN1 is just as an acronym that we have used. This is a homemade biochar made by using the coffee powder. So the residual coffee powder coming from the bars where you drink coffee were pyrolyzed at 700 degrees, and we obtained this biochar. Then the Merck is the name of the company from which we bought this biochar, and LP39 is another commercial biochar. So we compared two different commercial biochars with one homemade biochar. This slide shows the 19F NMR profiles of the garden in equilibrium with these three different solid phases. And what is clear from the left part of this slide is that the biochar that we have called LP39 shows in the whole Larmor frequencies, fluorine Larmor frequencies, shows the largest R1 values, while the other two biochars, Merck and APN1, so this is, just to remind you that this last one is the homemade one, appear very similar to each other. From a qualitative point of view, we could explain this behavior by saying that the biochar that we have called LP39 is the biochar that shows the highest affinity for these fluorinated organic compounds, while the other two biochars shows the same behavior when they are in contact with the fluorinated compound. And from a mathematical point of view, we also obtained the correlation times that confirm, as you can see to the right side of this slide, confirmed the hypothesis that we have done. So, which is the lesson that we can learn from these experiments? That among the different biochars that we use, there is at least one biochar that shows a very high affinity for the fluorinated compound. So very conceivably, we can use these biochars to try to remove the fluorinated compounds from water and soils. So this is the first conclusion that we can reach by using these different experiments and these different biochars. So from this point of view, we can say that the fast field cycling, the relaxometry, was very useful in let us understand which is the best biochar we can apply for this remediation. But another question came out. Okay, what happens if instead of using a fluorinated compound, we use simply water? So we use water as a polar model compound to understand if the behavior of this liquid on the surface of the different biochar changes, and then we can get different information. We also did these experiments, and surprisingly, we saw these, what you see in this slide. The Merck sample, so the biochar called the Merck, remained in the same position as before, more or less, while the NMR curves profiles from the LP39 and the APN1 biochars changed completely. Actually, what we saw is that the homemade biochar showed a very good affinity for water as compared with the LP39 biochar. So, and this was also confirmed by the quantitative evaluation of the correlation times that you can see to the right side, on the right side of this slide. So, which is the conclusion that we can have from these other sets, this other set of experiments? The conclusion is that the Merck biochar is useless for our purposes, so we can throw it away. But the nice, at least at the moment, the nice conclusion is that while we can use the biochar L39 to remediate from organic pollution, at least from fluorinated organic pollution, we can use the homemade biochar to remediate from polar pollutants. So we can have among these three biochar, two biochar that can be used for different purposes. One can be used for organic pollution, from polar organic pollution, and another one, the second one, the homemade one, can be used for the remediation from the very polar pollution. So, for example, we could use this second biochar, this homemade one, to remove heavy metals from water or from soils. Of course, this is just an hypothesis that has been done by using these experiments, and we are still to verify if these hypotheses can be really realized. So the question now is, which is the difference among these biochars? Why they behave so differently when we use the fluorinated compounds and water? Well, we did different experiments, as you see from this slide, and the DP mass C13 NMR did not show so many differences. At least the three biochars are typical biochars with a lot of polyaromatic systems, while the FTIR shows really very big differences among these three biochars that can justify the different behavior in respect of the water and fluorinated compound that we have used. Which is the conclusions that we can have from these? I hope that I'm in time. It seems yes. Which is the conclusions that we can have from these experiments? Well, the first conclusion is that fast field cycling NMR relaxometry is really a very promising technique to monitor environmental problems. There are, for example, very recently, we published a paper on the FFC NMR relaxometers applied on nanosponges that can be used to trap contaminants from water and soils, or can even be used to drive drugs into the organism. And the results were very interesting in terms of NMR behavior. We also let me say, saw the quadrupolar dips that Danuta showed this morning, and we were able to associate the changes in the areas of the quadrupolar dips to the amount of nitrogen that is present inside the different nanosponges that we analyzed. So as you see, this technique can be really applied very well in this environmental field. But which is the problem? That the environmental field at the moment is not in the hand of chemists, or at least physical chemists. That means that the use of this technique is considered too difficult for many people, and is too, let me say, our population, like our biodiversity, is very small as compared to the one that is needed to improve the use of the technique. But let me say, one positive thing is this cost action that is led by Danuta, that by using this new tool to communicate among each other, can, let me say, improve really the knowledge about this technique, and to decrease the fear that the people can have for quantum mechanics and the technique. So I do really hope that we can be able to spread much more this technique around the world, as at least as well as the normal NMR spectroscopy. Of course, I hope, this is just a hope for the future applications, but let me say that what I'm seeing at the moment seems to go in this direction. So let me say that I annoyed you very much, and I guess that we can I can finish my presentation, and thank you for your kind attention.